Good morning. Welcome to Krishna's classroom. Now we introduce the so-called LP spaces. Before that, let us recall what we did in the last lecture. We constructed RAB consisting of all Riemann integrable functions on the closed bounded interval. Thus, f belongs to RAB implies, because of the integrability function, integral a to b mod ft t finite. Now, this collection is a linear space, the usual addition and scalar multiplication. Now, on this linear space, we define a functional using the integral, and this is denoted by norm f1 defined by integral a to b mod ft dt. Now, this defines a semi-norm on RAB in the sense that it satisfies all the conditions of a length functional, but it fails to satisfy the first condition, namely that norm f1 equal to 0 implies f equal to 0. That means even if f is not equal to 0, norm f1 is 0. Now, this is because the problem that is inherent in the Riemann integrability. You see that a function which is 0 everywhere on the interval AB except on a null set. Now, this is the terminology that we have introduced while working on Riemann integration. Except on a null set. For instance, any countable subset. Its integral is going to be 0. Okay. And also, if you have two functions which differ only on a null set, and if they are integrable, then their integrals, their norms or their semi-norms that you define are the same. So, this is something that you have. Therefore, it falls short of a norm, and therefore, we have R, AB is not a normally linear space. That's a sort of inconvenience. Now, here what we did was, we introduced a relation among functions of R. So, we said f is related to t if and only if set of all x is then we proved that this is an equivalence relation. What is the consequence? The consequence is that it induces a partition on so let us designate with f the set of all G G is related to F. In the sense in which we have defined it earlier. Now this actually breaks up RAB into disjoint subsets. It's a union of disjoint subsets. Now bracket F consists of the block to which F belongs. It could as well be written as block G if G belongs to that class. Okay. So you see that block F is equal to block G if and only if otherwise there is no common element. So that partitions RAB into classes. This is block F. This is block H. And so on. Now on this collection, let us call this collection array. Then we can define this we have done earlier, but I am just recalling it. F plus G all these are well defined because given F and G, F plus G is defined. It's an element of RAB and there is a block to which it belongs to, and that block is identified as the sum of F with G. So alpha of block F is defined as the block alpha now with this addition and scalar multiplication, R tilde AB is a linear space. Okay. Is a vector space. And these sums are well defined. That means if that is therefore it is immaterial which particular representative element you use to work out the sum. So also therefore the sum and scalar multiple are very okay. So what if? Therefore this is a vector space. This is important. Now on this, then one can show that first we have to see that we say that f is the zero elements R tilde AB if the zero function. Okay, that is zero. So this turns out to be the zero element of R. It's a non-linear space. Now it induces a metric on namely minus. So this defines the distance function. Now what we have seen is that not complete. That is, Cauchy sequences in may not converge that's a problem. So lack of completeness makes the operations of analysis very difficult. Okay, so this is one problem. So what have we done? We started with a classical definition of integral as the antiderivative, which of course was good enough, but then we found that it gave no insight into what was happening. So with the introduction of Riemann integration, we could give a geometric interpretation to the whole idea. So now it becomes more visible and meaningful. And you see that a large class of functions could be now integrated. That's what we have observed. And then we defined what are called the Riemann integrable functions on the closed bounded interval AB. And with all these, we found that the space R tilde that you can construct out of it is not a complete metric space. Now this is one shortcut. Therefore, so this is one very strong reason why we went on to introduce or to take the whole concept of integration to the drawing board again and rework on this. And what kind of reworking we did? Introduce very sophisticated ideas like introducing a measure or what is called the Lebesgue measure, and then redefining what the integral is, and then we explored the properties of the new concept of integration. We did an elaborate work of that, and eventually we come back to the same question, like R tilde AB. What is the analog of R tilde AB with this particular new concept of integration? And then, in fact, we can build a whole scores of spaces with that. So, in fact, you have the entire class of spaces for various values of P, namely 1 less than or P less than or and it was found that the spaces so constructed with the appropriate norm defined become what are called complete normed linear spaces, which makes our work absolutely fruitful. All the objective that we were, all the advantages of completeness could be now made use of. And in fact, all Riemann integrable functions on AP are also Lebesgue integrable functions on the same set. And the analogous work that we do would enable us eventually to prove that LP is. This is the theme of our. So now let us start with the, what are called systematic definitions and so on, and also in all generality, rather than just defining it on intervals, we will work with what are called measurable subsets of R. Okay, so that's our task. So we define so now we take up the LP spaces. Let us introduce the appropriate notation. We define a measurable any measurable subset of R. Let F script F designate the set of all F where F is a measurable function, a measurable real valued function on it. Now, here again, this class is with the usual addition and scalar multiplication a linear space. Now, on that, we identify certain elements as the same. How do we do that? Well, we say that as follows. We say that F is related to G provided Fx equal to Gx for almost all x belonging to this is the definition. That means what you have is this, the set of all x zero. Now, one can easily show that this is an equivalence relation. and partitions F into equivalence classes. It's a small exercise. We shall denote this class the space of all equivalence classes of okay. We use this. That's a now one can introduce addition and scalar multiplication. That is as we did in the case of Riemann integrable functions. And so also alpha f, the block corresponding to alpha f, is identified as alpha times the block corresponding to alpha times the block corresponding to f is defined as the class, the block corresponding to alpha. Now that's a definition of addition and scalar multiplication. These definitions well defined. Irrespective of the representing functions used to identify the blocks. Now, as in the case of Riemann integration, that's very easy to verify. that is G1 and what's the meaning of that? So these are well defined. Now the zero element of consists of set of all f is 0. That is that's the zero element. And with this is a linear space. So we define what is called a once again one can show that F linear subspace of now this is in the case of p equal to 1. But for other p, some sophisticated results, sophisticated inequalities. Inequalities to prove it. This we shall take up later. But for case p equal to 1, or f finite, that is L1. Now what we have to verify in this case is that L1b is a vector space. So we shall observe that L1 is it is sufficient to show that if and alpha belonging to R. Now this needs, you see that this has to be in L1. So we have so we claim that Now, mod F, sorry, block F plus block G is block to which F plus G belongs to. Okay. Now, what we want to prove is, so it is that is fine. So, how do we prove this? Now, you see that mod A plus B therefore Fx now linearity of integral and monotonicity assures that so what we wanted to prove we have proved. Okay. Therefore, L1E is a vector space. It's closed with respect to addition and scalar multiplication. Okay, so also which is fine. So we have proved both of them. Now what next? Now we introduce the space called N. Well infinite. So for that, we introduce what is called essential. We say that F belonging to essentially bounded provided there exists M positive called the essential upper bound of F for which such that for that is set of all x for which zero. So precious. So we denote the following notation. But of course, that's old notation that F bounded on and F is Okay, that means the set on which G and F differ has measure 0. That's the meaning. That is the measure of we shall make some observations. Okay, I think that's a nice place where we can stop and then continue with this in the next lecture. Thank you very much.